Welcome to the deep dive. This is where we take your learning materials, boil them down, and help you get smart on a topic fast.
Yep, a shortcut to the essentials.
Today, we're diving into the foundations of information technology. We've got a great course summary someone sent in,
Mhm.
and our mission is really to uncover some, well, surprising origins and connections in the tech you use every day.
Absolutely.
hmm
It's about seeing that digital world, maybe, in a new light.
So we're not just talking definitions here.
No. We're tracing the history, the DNA of it all.
hmm
This summary, it covers a huge range.
Right, like what even is a computer? It's history.
Digital logic, the hardware itself, operating systems, networking,
Troubleshooting, too, for when things go wrong.
which they inevitably do. It's a really broad overview.
It really is, and you see how each layer kind of builds on the last one. It's fascinating.
Yeah, the past definitely echoes in the present tech.
And we've got some cool things lined up. Like, did you know old textile looms are connected to your laptop?
It sounds wild, but it's true.
Or why we still use this kind of inefficient keyboard layout.
The QWERTY story, yeah.
And we'll even find out about the actual bug that gave us the term debugging.
A literal insect. It's a great story.
Okay, let's dive in. First stop,
No.
the historical roots of computing.
Right. And maybe the best place to start is what is a computer? Seems simple, right?
Right, but maybe not so simple when you dig in.
Exactly. The definition we have here is, well, a device that stores and processes data,
Okay.
and it does that using calculations. Now, that seems obvious today,
Yeah.
but historically, the word computer, it actually meant a person, someone whose job was doing calculations.
Wow. Okay. That really puts the change in perspective.
Doesn't it? That whole shift highlights the massive transformation.
And it makes you think everything we do online, social media, games,
Looking things up.
it all boils down to those calculations happening underneath.
Yeah. And understanding that history, from people calculating to silicon doing it, gives you context for why tech works the way it does now.
Totally. So what were the early steps? The summary mentions early tools.
Yeah, it starts way back, the abacus, like 500 BC.
Still used in some places, right?
Amazingly, yes, for counting large numbers. Then you fast forward a bit, centuries later, you get more complex counting machines, but still manual.
Okay, until automation starts creeping in.
Exactly. Big step. Blaise Pascal, 17th century, his mechanical calculator.
What made it special?
It used gears, levers. It could actually do basic math automatically. Limited, sure, but automatic.
Okay, so that's cool. But the textile industry connection, that seems like a leap.
It does. But those mechanical principles, they got applied there. Early 1800s, Joseph Jacquard, he invented a programmable loom,
Programmable? How?
punched cards. This is like foundational. A hole meant on a hook engages a thread. No hole meant off, no thread.
So that's binary. On, off, hole, no hole.
You got it. That exact concept, hole was picked up later for computers, refined into the one and jewel we use today.
That's incredible. A weaving machine basically setting up binary.
Yeah, it shows how these abstract ideas pop up from really practical needs. You see that pattern again and again in tech history.
Mind blown already. Okay, so the summary moves on to World War II next. Sounds like another big jump.
Huge jump. Before the war, like you said, funding was an issue, research was slow, components were physically enormous.
Room-sized computers, literally.
Exactly. But the war, well, strategic needs changed everything. Government started pouring money in.
Why? What was the advantage?
Processing information fast. Think cryptography breaking codes. Computers could do that way faster than humans.
Ah, code breaking. Makes sense.
And that wartime focus on crypto, it directly leads into modern computer security. It's all connected.
Necessity, mother of invention, indeed. So the war ends, but the progress doesn't stop.
Not at all. Post-war, you had companies like IBM, HP, plus governments, scientists. Everyone kept pushing.
And storing data became a bigger deal.
Yeah, because they were generating more of it. Punch cards were still around. You had these ordered decks.
Imagine dropping one.
Ugh, nightmare. Reordering that, forget it. Then, the 1950s, magnetic tape comes along.
Like cassette tapes.
Sort of, yeah. Storing data by magnetizing tape. Way more reliable, started pushing out punch cards.
Okay, so storage is getting better, but the size thing, these machines are still massive, right? You mentioned components earlier.
Yeah, huge. Early computers used vacuum tubes to control the electricity. Thousands of them.
Like old radios or TVs.
Exactly. And they weren't just big, they failed constantly.
So early IT support was just changing tubes.
Pretty much. Changing tubes, managing punch cards. And that's where debugging comes from. It's a literal story.
The moth story, tell it.
Okay, so Admiral Grace Hopper's team, working on the Harvard Mark II, they found an actual moth stuck in a relay causing problems.
No way. A literal bug?
Yep, they taped it into the logbook, hence debugging.
That's fantastic. And the scale. The ENIAC computer.
Oh, enormous.
Yeah.
Took up like 1,800 square feet, had around 17,000 vacuum tubes.
It's hard to even picture that.
Totally.
How then?
But then transistors. That was the real game changer.
Smaller.
Way smaller. They do the same job as tubes switching electricity, but tiny, use less power, much more reliable.
And we still use them today.
Fundamentally, yes.
Yeah.
Billions of them on a single chip now. It's incredible miniaturization.
And Grace Hopper pops up again? With compilers?
She does. I pioneer.
Yeah.
She invented the first compiler.
Okay, explain compilers. Why was that so important?
Think of it like a translator. Programmers could write in languages closer to human language.
Easier to understand.
Right, and the compiler translates that into the basic machine code the computer actually understands.
Yeah.
Ones and zeros again.
So it made programming way more accessible.
Hugely. Opened the door for all the software we have today. Before that, it was super low-level, cryptic stuff.
Got it. And things kept shrinking. Hard drives, microprocessors.
Yep. Hard disk drives for storage, then microprocessors putting the whole CPU onto one chip. That constant shrinking, plus more power.
Leads to smartphones in our pockets being more powerful than those old room-sized giants.
Exactly. Pocket-sized powerhouses. And of course, IT support changed dramatically along the way. Less tube swapping, more software issues.
Which brings us nicely to the next big topic. Digital logic.
Yeah, the language computers actually speak.
Okay, so you said it's all ones and zeros underneath, billions of comparisons a second.
Pretty much. That's the core. The system they use is binary. Base 2, just 2 digits, 0 and 1.
Like our alphabet makes words, binary makes data.
Good analogy. Combinations of zeros and ones represent everything. Text, numbers, images, sound.
And a single 0 or 1 is a bit.
Correct. Smallest piece of data. But they're usually grouped together.
Into bytes?
Yep, the standard group is 8 bits. That's a byte.
Yeah.
Which kind of became the standard over time.
And 1 byte can store, what, like 1 letter?
Usually, yeah. One character, a letter, a number, punctuation. And since each of the 8 bits has 2 possibilities,
2 to the power of 8.
is 256. So a byte can represent 256 different things. You might see it written like, I don't know, 111.
Okay, so we have bytes. 101, 1011. How does the computer know that means H or something?
Ah, good question. That's character encoding. It's like a code book, a dictionary.
Translating binary to characters we read.
Exactly. ASCII was one of the first big ones. Handled English letters, numbers, basic stuff. Used 127 values within a byte.
But only English, basically. Seems limited.
It was. As soon as you needed other languages, accented characters, symbols, ASCII wasn't enough.
So what do we use now?
Mostly UTF-8. It's clever, includes all the old ASCII characters, so it's compatible.
Okay.
But it can use more than 1 byte if needed. So it can represent characters from pretty much any language, plus symbols, emojis, all that stuff.
Emojis run on UTF-8.
They do. It's based on the bigger Unicode standard, which tries to give every character a unique number. It's pretty amazing, really trying to encode all human language digitally.
Wow. Okay, text covered. What about colors on screen?
Usually models like RGB, red, green, blue. Computers often use 3 bytes, 1 for the intensity of red, 1 for green, 1 for blue. Mix those together, and you get millions of colors for each pixel on your screen.
Got it. So binary represents the data. But how does the computer do things with it? Physically.
Well, think back to that loon. On, off, right? Hole in a hole. It's the same idea. Binary states.
Right.
Today, it's electricity and those tiny transistors. Voltage present, that's a 1 or on. No voltage, that's a 0, off.
Simple on-off switch, electrically.
Fundamentally, yes.
No.
But you need more than just on-off. You need logic. That's where logic gates come in.
Built from transistors.
Yeah. They perform basic logical operations, AND or ERA, not directing the flow of electricity based on the zeros and ones coming in.
So the gates are doing the actual thinking, the comparing.
In a way, yes. They manipulate the binary signals. That's what lets the computer calculate and run complex tasks.
Okay. And you mentioned base 2 versus base 10. We count in tens, computers in twos.
Right. We use decimal, 0 through 9. Computers use binary, 0 and 1.
And the summary says IT folks need to understand how to convert between them. Why?
Sometimes you need to look under the hood, see what the computer's actually dealing with for troubleshooting or low-level stuff. You might need to translate that binary back to decimal.
How does that work?
It's about place value. In an 8-bit byte, reading right to left, the places are worth 1, 2, 4, 8, 16, 32, 64, 128. Each place is double the one before it.
Powers of 2.
Exactly.
Yeah.
So if you have a binary number, you just add up the values where there's a 1.
Give me an example.
Okay, 0, 1, 1, 1, 1000. That's H in ASCII. You got 1s in the 64's place, the 32's place, and the 8's place.
So 64 plus 32 plus 8.
Equals 104. That's the decimal value. And an 8-bit byte can represent any decimal number from 0 up to 255.
Right, because 11111111 would be 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1.
Exactly, 255. So any number can be represented with just bits.
Okay, binary makes more sense now. Language, logic, numbers, all zeros and ones. So next up is computer architecture, the overall structure.
All right, and most users, they just interact with the top layer, the apps.
Clicking icons, using software.
Yeah. But for IT support, you need to know what's happening underneath that surface. For troubleshooting, maintenance, performance.
Got to understand the whole system.
Exactly. And we could think of it in like 4 main layers, conceptually.
Layer 1.
Hardware, the physical stuff, laptop, phone, monitor, keyboard, the chips inside the box, things you can touch.
Yeah, layer 2.
The operating system.
Yeah.
OS. That's the software that manages the hardware, lets it all talk to each other. Windows, Mac OS, Linux, Android.
The conductor of the orchestra.
Nice analogy.
Yeah.
Layer 3 is software. Your applications, your programs, web browser, word processor, games, even parts of the OS itself, what you actually use.
And the last layer.
The user.
Yeah.
You. The person interacting with it all. The human element. Super important for IT support, obviously.
Right, because problems often involve understanding what the user did or needs. Okay, so layers. Let's dig into that bottom layer. Hardware.
Okay, so outside the box, you've got your common ports. USB, 2.0, 3.0, the newer Type-C ones.
Which are great, one plug for everything.
Pretty much. And display ports, DVI, HDMI, DisplayPort for connecting monitors. But the real action is inside the case.
What are the core components in there?
Okay, first, the CPU, Central Processing Unit. The brain.
Does all the calculations?
Yep. Processes the data, talks constantly to the RAM, uses its own set of basic instructions. Intel, AMD make most desktop ones. Apple, Qualcomm for mobile.
Different brands, but same basic job.
Pretty much, yeah.
Yeah.
Different instruction sets maybe, but similar function. Next is RAM. Random access memory.
Short-term memory?
Exactly. Quick access, but temporary. Volatile loses data when power's off. When you run a program, it loads into RAM so the CPU can grab it fast.
More RAM means more programs at once, generally.
Generally, yes.
Yeah.
Less slowdown.
Yeah.
You see types like DRAM, SDRAM, DDR4. They come on little sticks called DIMMs that plug into the motherboard.
Okay, CPU is the brain, RAM is the scratch pad. Where does everything live long term?
That's the hard drive. Or, more commonly now, solid-state drive, SSD, persistent storage.
Music, photos, the OS itself.
Everything. Data stored in blocks on the drive. And there's data about the data, like when was the file created, what type is
How
it.
does it connect?
Older ones use Molex for power, but now it's mostly SATA connectors for power and data. Much simpler.
And connecting all of this together, that's the motherboard's job.
You got it. The motherboard is the main circuit board.
Yeah.
Everything plugs into it. It's the foundation, lets components communicate.
Compatibility matters here, right? CPU socket, RAM slots.
Hugely. CPU needs the right socket. RAM needs the right type of DIMM slot. Motherboards also have chipsets controlling communication and expansion slots like PCIe for adding things like graphics cards.
And they come in different sizes, ATX, ITX.
Yeah, form factors.
Yeah.
Affects how many slots you get, what case you need, and all this needs power.
The power supply unit, PSU.
Right, converts AC wall power to the DC voltages the computer needs. Crucial to have enough wattage for all your components. And always use the right voltage for your region. Don't want to fry anything.
Definitely not. Okay, it's like a tiny city in there. How does data actually flow between these parts? Like when I start a program...
Okay, simplified view. Program's on your hard drive, right?
Yep.
You launch it. A copy gets loaded into RAM.
For faster access.
Exactly. The CPU needs instructions from RAM. But RAM can be big, so there's a helper. The memory controller chip, MCC.
A traffic cop for memory.
Sort of. CPU asks the MCC for data at a specific memory address using the address bus. MCC finds it, sends it back to the CPU over the external data bus or EDB.
And the EDB is just wires carrying voltage.
Yep. That's our ones and A's again as electrical signals.
Yeah.
Inside the CPU, it has tiny, super fast storage spots called registers to work with the data immediately.
And cache. I hear about L1, L2 cache.
Right. That's even faster memory, right near or on the CPU. Stores frequently use data so the CPU doesn't even have to wait for RAM. Speeds things up a lot. L1 is fastest smallest, L3 is slowest biggest of the caches.
And the clock speed? gigahertz.
That's the pacemaker. Sets the rhythm for all these operations. Higher gigahertz means more cycles per second, so potentially faster processing. And lastly, things like keyboards, mice, I/O devices.
How do they talk to the system?
Through the operating system's core, the kernel, using special software called device drivers.
Phew. Okay, that's a lot of interaction. The summary even mentions building a PC. ESD safety is key. Static electricity.
Oh, absolutely critical. Static discharge can kill components instantly, even if they're not powered on.
So ground yourself. Use a wrist strap.
Definitely. Touch grounded metal, use a strap, keep parts in their anti-static bags until you need them. Then it's motherboard in the case, CPU cooler on, RAM in slots, storage mounted, any extra cards like graphics.
Plug in the PSU cables.
Right. Connect to everything that needs power. Then peripherals. If you turn it on and get something on the screen, that's usually a good sign.
Fingers crossed. But what if it doesn't boot? Hardware troubleshooting.
Yeah, understanding the boot process is key there. When you hit power, the BIOS or UEFI firmware wakes up.
Basic input-output system? Or the newer UEFI?
Right. It initializes hardware, then runs a piece power on self-test, checks CPU, RAM, basic stuff.
What if P-post fails?
You might get beep codes, like Morse code for errors. You need the motherboard manual to know what the beeps mean.
Okay, assuming POOST passes.
The BIOS UEFI looks at the boot order you set. Which device should it try to load the operating system from first? Hard drive, USB.
It's looking for the OS loader program.
Exactly, the bootloader. And those settings, boot order, date time, are stored on a little chip called CMOS, usually powered by a small battery on the motherboard.
And you can change those settings.
You usually hit delete or F2 or F12 right at startup to get into the BIOS UEFI setup menu. IT pros do this all the time, maybe to boot from a USB to reinstall Windows or run diagnostics.
Makes sense. Okay, that covers hardware pretty well. Moving up a layer now to operating systems, the OS.
The crucial middleman. Makes the hardware usable, lets software run, manages everything.
And the summary says understanding one OS helps you understand others, like desktop versus mobile.
Yeah, the core concepts are often similar. And at the very heart of the OS is the kernel.
The core manager.
Right. Controls resources. Think of its main jobs. File management is huge.
The files are stored, organized?
Yep. The file system structure folders, directories, how data is physically put onto the disk in blocks, the metadata about each file name, size, date.
And different OS use different file systems. NTFS, ext4.
Right, and they aren't always compatible. File extensions, .txt, .jpg, help the OS know what type of file it is.
Okay, file management. What else does the kernel do?
Process management. A program is just a file on disk. When you run it, it becomes a process.
A running instance of the program.
Exactly. The kernel manages all running processes, gives them RAM, CPU time,
Okay.
uses a scheduler to juggle them, making it seem like they're all running at once, multitasking.
So if my computer's slow, it might be a process hogging resources.
Very possibly. Too many processes, or one using way too much CPU or RAM. Then there's memory management optimizing RAM use.
Making sure apps get what they need without stepping on each other's toes.
Right. And input-output, I/O management. Talking to your keyboard, mouse, monitor, disks.
Using those device drivers we mentioned.
Yep. Managing data flow to and from peripherals. I/O bottlenecks can also cause slowdowns.
So the kernel is busy, but we don't talk to it directly, right? We use...
The user space,
Yeah.
everything outside the kernel. Mostly we interact via a GUI graphical user interface.
Windows, icons, menus, pointers, clicky stuff.
Exactly. Desktops, phones, tablets, ATMs. GUIs are everywhere, but there's also the shell.
The command line. Black screen, text commands.
That's the one. It interprets text commands you type. It was the only way before GUIs. Still super powerful, especially for IT pros, managing servers remotely, automation.
Linux uses shells a lot. Bash.
Yep, Bash is a very common one. Knowing shell commands is a really valuable IT skill.
Okay, GUI for visuals, shell for text commands, and when things go wrong, logs.
System logs.
Huh.
Crucial. The OS records tons of events. Startup, shutdown, errors, driver loads. It's like the computer's diary.
It's a troubleshooting.
Logs are invaluable. They show what happened when. You can trace events, find error messages, figure out what went wrong.
On a computer's diary, I like that. Okay, moving on to networking. Connecting everything up.
Right, and the internet. It's not a cloud, it's just a massive network. Billions of computers connected globally.
Allowing them to talk to each other, exchange data.
Exactly. Networks can be simple to computers or crazy complex, like the whole internet or a big company's network.
And the World Wide Web, that's different from the internet.
Good point.
Yes.
The internet is the roads, the infrastructure, The web, www, is one way to use those roads, accessing websites via browsers using HTML.
Okay, we access websites using URLs.web addresses.
Yep. Domain name like google.com, ending like .com, .org. Registered via ICANN, that international body.
So how do devices find each other on this giant network?
Unique identifiers.
Yeah.
Two main ones, IP address and MSC address.
IP is like the house address, network location.
Good analogy, yes.
Yeah.
Tells data where to go on the network. MSC address is more like the specific mailbox at that address. A unique hardware ID for the network card used for local communication.
Okay. And data travels in.
Packets. Small chunks of those ones and zeros. Each packet has address info so it can be routed correctly and reassembled at the destination.
But we type names like google.com, not IP addresses. How does that work?
DNS, domain name system. It's the internet's phone book. Translates human-friendly domain names into the numerical IP addresses computers actually use.
So when I type a web address,
A DNS lookup happens behind the scenes. Your computer asks a DNS server, what's the IP for google.com? The server replies, and your browser connects.
clever. Okay, IP, MAC, DNS. How do we physically connect?
Common ways. Ethernet cable wired connection. Wi-Fi wireless uses radio waves. And fiber optic cables data as light pulses, super fast, often used for the internet backbone or high-speed business lines.
More expensive, though.
Usually, yeah. Higher speed, higher cost, generally.
And we don't plug straight into the internet backbone. We use routers, switches.
Right. A router connects your local network, home, office, to other networks, like your internet provider. It directs traffic using network rules, protocols.
And a switch?
Manages traffic within your local network. Smarter than old hubs. Sends data only to the intended device, not broadcasting it everywhere. Hubs were simpler, just repeated signals to everything.
And protocols, rules for communication.
Exactly. Network protocols are standardized rules for how data is formatted, sent, received, ensures it gets there correctly, securely, intact. The big one for the internet is TCP/IP.
Transmission Control Protocol Internet Protocol. Foundational.
Yep. Thanks to pioneers like Vint Cerf and Bob Kahn.
So, lots of moving parts to get online. Troubleshooting network issues. Where do you start?
Understanding the connections is key. You often work through the network stack. Start at the user's computer, check cables, check the switch, the router, work your way out.
Physical first, then devices.
Often, yeah. IP addresses help checking server logs, for example. And DNS is a really common culprit for website access issues.
Like you can reach the IP, but not the name.
Exactly. That points straight to a DNS problem.
Very helpful. Okay, let's shift to software, the instructions that tell the hardware what to do.
Right. Software, programs, applications, terms often used interchangeably. It's just instructions for the computer.
Early on, that was punch cards, binary code.
Yep. Then assembly language, a bit more human-readable, mnemonics for instructions, but still very low level and tied to specific CPUs.
Hard to write for different computers.
Exactly. That's why compiled languages were a big deal. Writing something closer to English.
Like C++ stuff, Java.
Right. Then a compiler translates it into the machine code for a specific CPU type. Remember Grace Hopper?
Her compiler made software portable.
Huge step. Then you also have interpreted languages, like Python, JavaScript. The code, a script, is translated on the fly, line by an interpreter program when you run it.
So coding, scripting, programming, all related.
Yeah, basically writing instructions. Coding is general. Scripting often uses those interpreted languages for automation or simpler tasks. Programming can imply more complex application development. Anyone who knows a language can write code.
And for IT pros, understanding how software works, installs, fails, that's essential.
Absolutely. Installation, configuration, errors, day-to-day stuff.
How does software get to us, and what are the rules? Licensing.
Yeah, distribution and licensing. Software is usually protected by copyright. Developers choose how to distribute it.
Like commercial software. Pay for a license.
Right. The license tells you what you can and can't do. Then there's open source software.
Free to use, share, modify.
Often, yes. External LibreOffice, Firefox, big examples. Code is shared openly, often developed by a community. But even open source has licenses defining terms.
So always check the license agreement in IT.
Always. Got to comply with the terms.
Okay. And different types of software based on function?
Broadly, yeah. Application software meets user needs.
Yeah.
Word processors, browsers, games.
What we normally think of as apps.
Right.
Yeah.
System software keeps the system running. OS tools, utilities.
Background stuff.
And firmware, software embedded right into hardware, like BIOS Z5. Handles basic hardware startup.
And software gets updated. Regions?
Yep. Version numbers, 1.1, 2.0, track changes, New features, fixes compatibility, and crucial security patches.
Security updates. Important.
Hugely important. Running old, unpatched software is a massive security risk. Known flaws get exploited. Best practice, keep everything updated.
Makes sense. Managing software across lots of computers must be tough, though, manually.
Oh, impossible manually at scale. That's why IT uses automation tools, software management programs, scripts to deploy, update, remove software efficiently.
Scripts for log analysis, too, maybe.
Sure, lots of uses. It's about efficiency, ensuring people have the tools they need, removing stuff they don't, and keeping things secure.
And testing updates before rolling them out widely.
Critical. Test in a sandbox first. Avoid breaking things for everyone, and preventing users installing random stuff.
Malware risk.
Right. Usually need admin rights to install software, and always get it from reputable sources only. Standard security practice.
Okay, solid overview of software. Last big topic, troubleshooting. The art of fixing things.
Essential skill. Diagnosing, resolving issues, technical problems, user problems. It's constant in IT.
And the big mistake is fixing before diagnosing.
Exactly. Jumping to solutions without understanding the actual problem. Treating symptoms, not the cause.
So, what are the good techniques? The summary lists a few.
Key ones, yeah. First, ask questions, gather data. Sounds obvious but critical. Don't go on autopilot. Get all the info. What happened? When? Error messages. What did the user try?
Avoid assumptions. Be tactful.
Absolutely. User experience matters. Second, follow the cookie crumbs. Investigate the history. When did it start? Any changes? Check those system logs, error messages.
Look for clues.
Right. Third, isolate the problem. Narrow it down. Rule things out. Focus on the likely cause. Don't boil the ocean.
Makes sense. And fourth,
Start with the quickest step first. Try the easy fixes first. Check cables. Reboot. Simple stuff. Saves time if it works.
logical steps. And the ultimate goal is finding the...
Root cause.
Yeah.
The real underlying reason for the problem, not just the symptom.
Why is finding the root cause so important?
Because if you only fix the symptom, the problem will likely come back. Fixing the root cause prevents recurrence. Wiping a system might fix it temporarily.
But you don't know why it broke.
Exactly. Doesn't help long term. Methodical testing, isolation, that leads you to the root cause.
Are there common mistakes troubleshooters make? Pitfalls.
Definitely. Going into autopilot is one. Thinking, oh, I've seen this before. Always ask questions, gather fresh data. Small differences matter.
And the other big one?
Not finding the root cause. Getting stuck fixing symptoms. Focus on the why. Avoid those quick fixes like wiping without understanding.
Great advice. Well, that was quite the journey. From ancient counting tools to modern networks and software, and how to fix it when it breaks.
It really covers the fundamentals. And seeing how it all connects gives you real insight into the tech we use constantly.
Yeah, those historical links were amazing. The Loom connection.
And the literal bug. Can't beat that.
Definitely memorable. And obviously, we just scratched the surface here. Each area, logic, hardware, OS, networking, software, troubleshooting, you can go so much deeper.
Oh, for sure. Hopefully this sparks some interest for people to explore areas they found intriguing.
Absolutely. So maybe a final thought to leave everyone with.
Well, think about how those historical forces, those basic principles we talked about, are still shaping technology today. What things that we use now? Maybe things that aren't even perfectly optimal.
Like the QWERTY keyboard.
Exactly. What current tech standards might future generations look back on and think, wow, why did they do it that way? It makes you wonder what's next, built on these same foundations.
A really thought-provoking question. Thanks for that deep dive today.
My pleasure. Lots to think about.